It's okay, or is it flaky? Okay, all right, we'll see what happens. All right, so I wanted to actually talk a little bit about assignment 1 as well as assignment 2 today, but we'll get to that as we go. What I'd like to do, of course, also today is to talk at some great length about some of the... Hello, you can do it. Yeah, sorry, my fault. It helps to actually plug in. So for once, I can't blame the system. Yeah, there we go. All right, so you can see why I'm asking those questions. All right, so what I wanted to do was to talk a little bit about assignment 1 as well as assignment 2. I'll defer the consideration of assignment 1 because I wanted to actually access the thing at cab302.bitbucket.org, which we may actually be able to get hold of now. We'll just see, since I may actually have access back again. So let's see if we can do that. Let's go to... Okay, so let's begin with this. I don't want to spend a lot of time talking about the assignments today, although we will spend a little bit of time on them. The main reason for that is that we have a very packed lecture, which I want to get through, and I want to talk about some very specific things. Just pay particular attention to what I say as I'm lecturing today, because the threads lecture is very, very important, but there are a number of things in there which I think it is necessary to expose you to, but are not going to be highly examinable, okay? So I'm going to tell you which bits are very, very important and which bits are not important. I mean, all of the stuff that's in today's lecture is important to your development as professional programmers. Otherwise, it wouldn't be in the lecture. But there's a bunch of stuff in there which I want to focus on, and a bunch of stuff in there, particularly the stuff around waiting and notifications and so on, and daemon threads and things like this, which are not especially important as far as this semester is concerned. So, pay particular attention to this as I talk our way through it. In terms of assignment 1, you've now all got your marks. Most of the marks have been very good. My inbox has had very, very few emails from students screaming blue murder about their assignment marks. Very few indeed, actually. And so that suggests that people are relatively happy with what they've got and relatively happy with the feedback. Can I just say categorically that if you have any issues with assignment 1, then of course follow the procedure that I set out when the marks were released. But I want to shut that all down by the end of this week, right? I have, on occasions, believe it or not, had students come to me after the release of the final results for the unit, seeking to have assignment 1 remarked because there was something that was wrong with that. The fact that the student was actually 1 or 2% below a grade boundary, of course, had nothing to do with the sudden interest in their assignment 1 mark. So basically, we don't revisit it. You've got to draw the line somewhere. Very happy to look through it. Very happy to examine the feedback and to make sure that the mark was appropriate given the quality of the submission. But you can't revisit something 50 years after the event, and so we won't be doing that. So I also just want to get that completely out of the way so that assignment 2 is the only thing on the agenda. All right? So if you have concerns about assignment 1, please talk to someone this week, and we will try and draw a line. I'll send something around via email about that as well. But I'd just like to draw a line on assignment 1 at the end of this week. That gives people a good week and a half or so to have a good look at the assignment and to see whether there are any issues. but most people have done that by now, I think, and most people seem to be relatively happy. Sam got a case of the alliterative use of the word C with commonly commented comments from assignment 1, and these are comments which are there basically about code quality and various other things. If you haven't looked at these, please do so. Some of them will have appeared on your own assignments, but this is essentially a grep. Okay? They basically went through and grabbed all the comments from the system that had been used on people's assignments and assembled them into this particular document, and then, of course, put them in under subheadings. So there's a fair bit of informative stuff here. You know, things about the constructor, things about exceptions. I looked before at these, and the ones about null pointer exceptions and so on, the distinction between an exception and an error. So things like null pointer exceptions, which obviously indicate a programming error, you know, you don't throw those, the system throws those, you don't catch those. If one of those comes along, then you've got a horror story which you have to fix. So these are things which, you know, you'll just get through experience as we go on, okay? Now, I've not released any podcasts in relation to assignment 2. I will get to those probably this evening. I also have to give you some indication in relation to the second part of assignment 2, which is, of course, the GUI. Now, I was hoping to get that out today, and we may still do so, but it's more likely to come out tomorrow or Wednesday. The reason for this is that we are looking at the use of automated GUI tests, and we believe that we can, you know, I said previously that we weren't going to do this, but we've had another look at it, and we believe that we can probably do it, and the plan here would be to not really require much of you in terms of assessing these things, but to actually provide you with some of our GUI tests and to, you know, give you instructions on how to put that all together. And that will then be part of the marking, but also part of your checking before you submit. So if you're not familiar with what I'm talking about here, an automated GUI test basically uses various test fixtures which mimic the actual swing fixtures, the actual swing widgets. And what you're able to do by essentially chaining methods, you're able to get the behavior that you would get through interactively working with the GUI. So, I mean, just to show you the sorts of things that we're talking about, I don't think I've got it open anymore. I think I blew it away. But if we look at something like fest swing, okay, so if we look at something like this, presuming it loads, there's a little bit of an example here in which we should actually be able to work with. Yeah, so here's a simple example which you can look at, but somewhere a little bit further down here. Do we actually have it? Yeah, okay. So, you know, here's window.textbox, text to copy.enter text, window.button, copy button.click. Okay, you may not be able to read that because of the font, but essentially what's happening is the things that the user would actually be doing with the widgets are done programmatically. And it turns it into a JUnit test, basically. So we're looking at the moment at just how easily we can make that available. And if it's painless, and we can just say, follow these instructions and include it in Eclipse, and basically you're good to go, then we will do so. Okay? Now, Mal has done some investigation of that and has it working for a simple class. It will mean that we'll have to constrain some aspects of the actual GUI, which we're already doing to some degree anyway. But I think it's probably worth it in terms of the quality of the stuff that you'll produce, giving you another string to your bow when you come to an employment interview. Have you ever used automated GUI tests? Well, yes, you will have by then, and you'll have actually written some. And hopefully that will make everything easier for everyone. The way we would do it, by the way, just to be clear about this, if we supply these things, then we will supply quite a number of them, and the way you would actually write tests would really be just to use what we've got as a template. So you wouldn't have to learn a whole new framework or anything. It's really quite straightforward. But it's something that we will basically find out properly in the next day or so and then push out the message from there. I will release, I mean, just to give you some idea, the assignment 2, part 2, contains an extensive guide to what I want you to do in terms of the construction of the GUI. It's really, I wouldn't describe it as straightforward, but it is something which you should find relatively easy to follow, and I don't think it will give you too much pain. So that podcast, there are a couple of questions about exceptions and so on, which people asked on Facebook over the weekend. I will put something out about those today. I haven't got to that yet. Mostly the answer to those is that in most of these cases, there's a deliberate choice to say that that validation is happening elsewhere. But I didn't want to make that comment until I'd had a very good look at it, just to make sure that we haven't missed anything. So just bear with me on that one, and I'll get something out about that in the next day or so. Any general questions about the assignment? Yeah.
Just with submission, you guys will be looking at our stuff on either Bitbucket or wherever it is. Is that right? Or are we...
The basic point is this: when you submit, we want a copy of your logs, right? Now, what we want is what we want you to be aware of is that when you submit, we want a copy of your logs, so it'll be a Git history or whatever you're using, and we're quite happy for that just to be included as a file. But the basic point is, if we look at that and we don't believe it, then we'll come to you and say, show us your log. Okay, so we'll either ask for you to add us as a team member, or we'll ask you to come and demo it and show us that your log really is real. Okay, so the basic point is, in most cases, we won't directly look at your logs, because we'll look at your log and we'll say, yes, we believe you. But when we don't, then of course, we will, ask you to show us evidence that it did actually happen that way. And but the basic point is, faking your logs is more trouble than it's worth. The other point, as I said before on that too, the criteria around around source control are really quite generous. So it's not something that I want you to be too concerned about. And as I've said to you previously, just commit, right? Don't be worried about having a massive number of commits. It's not an issue. If you're doing stuff and you make a mistake and you need to fix it, well, it's a commit. If you decide, that you've done this bit, then it's a commit. It's not something. What I don't want to see is, started assignment, git init, April 29, and then I see the first commit on May 27. That's not the sort of history that I'm looking for. Okay, and that's the sort of thing that I want you to avoid. Just get into the habit of using it, and so that it's a normal part of your development process. Okay? All right, so let me start this lecture. And this lecture contains a lot of stuff. And it's a good reference, this lecture, but you need a bit of a guide. And so hopefully I can provide that. I'm also going to spend a fair bit of time doing demos, or at least running a couple of demos. Can I make it very clear that those demos and the prac are very, very important? There's also there will also be an additional prac sheet based on this stuff, which is not released yet. And this will be released in the next day or two. And it concerns the use of threads around swing. Okay? And that's something which will be sort of a supplement to part 2 of the assignment. So it's basically intended to be something that you can work through at your own pace and then steal for the assignment. okay? Because there are particular ways that I want you to do things because it's the best way of doing it. Okay, so just to be clear about this too, this lecture is largely about threads. It's not about swing. So there are some things here that we do where we're just demoing things which we don't do properly, okay? And I'll explain that at various stages. What I'm talking about here specifically is that swing applications are supposed to be, if you're writing a genuine swing application, you have to be very respectful of a thing called the event dispatch thread. And if you're not respectful of the event dispatch thread, and you don't make sure that the events are actually processed on that thread, then you will end up with some seriously badly behaved swing applications. You'll get blocking, you'll get things not updating when they're supposed to, and so on. Now, the way to do this is to use a method which you'll find in a class called swing utilities, and invoke and run later, and invoke and wait, and so on. There are a couple of different options. But generally speaking, we will do that for our proper applications, but there's some stuff here where we haven't bothered. Okay, so just to be clear on that, some of this code isn't completely pure. So we'll talk about that later as we go. There's also stuff about swing workers, which are used for background threads in swing applications. Now, none of what we're doing in the remainder of this semester is sophisticated enough, or at least has sufficient processing load, that you really need a swing worker. But the swing worker is very, very important to you if you're actually writing something that's loading large files or something like that. So it's essential that you know about it, all right? And so there's a little bit at the end here where we talk about that. But for now, we're going to talk about threads. So some basic acknowledgements to Mal's earlier code and my earlier code. And then we get into this agenda. All right, so there's this ridiculous thing that we do. And the ridiculous thing that we do, which you need to be aware of, is that there are two ways of getting a thread in Java. The first thing is you already know a little bit about threads because I talked about them a few lectures ago. But you don't know much about threads. The first thing that you need to know is that threads in Java are associated, unsurprisingly, with a class called thread. Okay? However, we almost never use the thread class to deal with threads, or at least not directly. Why? Well, it's pretty simple, really. Java has this rule against multiple inheritance. What's multiple inheritance? Somebody? Yeah, a class which extends more than one class. Okay? So try it next time you're in Eclipse. Public class, my class, extends some other class, comma, some other class again. Okay? What happens? Well, the compiler ain't going to like it. It just doesn't happen. You cannot extend two classes in Java. It's just not permissible. So the point, of course, is that if you rely on extending the thread class to have the character of a thread, then you remove all chance of extending from a class that you really want to extend from. Is everyone following me there? So basically, you have one subclassing relationship that you can use. Okay? So if I have one subclassing relationship that I can use, well, I'd probably prefer to keep it for the frame or keep it for, my, container class or whatever it happens to be, right? I don't want to waste it on the thread because there are some things in this big class that I've written that I really want to use. And if I waste it on the thread, well, I have to sort of re-implement all of those. So what people do instead is, instead of using the thread class, they implement the Runnable Interface. Okay? But the way these things are set up, you still have to make it a thread in some way. So all of this is background and a bit of a preview of how all of this stuff comes together. All right? So that's why this lecture is so long in terms of the actual number of slides, because you'll get two versions of the first thing and then some explanation of the relationships between them. That's not that important in the grand scheme of things. Because in the end, you'll be dealing with the runnable interface all the time. You'll almost never use a thread directly. But you need to understand where all of this is coming from. All right, we saw our old César Franck, okay, the Panis Angelicus of César Franck. We recalled this idea that it's possible to go forward together at the same time, basically doing different things. Although in a small vocal group, we at least hope that there is some harmonic relationship between what the individuals are doing. But the key point is it's not just the tenor or the soprano blasting out in unison and everyone following them. All right? So what we've got is this possibility that people are doing different things and that they're cooperative in some way, but they're both going forward in time, or the four of them are going forward in time here, kind of independently of one another. Okay, our agenda. Programs, processes, threads. All right, so what's a thread? Okay, a bit of revision, perhaps new for some of you. The basic idea is that for an operating system, we have programs, okay? And associated with one or more programs, we have processes. So basically, if I have an operating system, I generally have a whole bunch of programs which are running, a surprising number you'll find. And each of those has a process ID. Each of them is a process. Each of them are independent in some way, though, of course, they all share the same resources. And that's, of course, the job of the operating system to manage those. Threads are processes within an individual program. End of story. Right? That is all you really need to understand conceptually. The rest of it is the mechanics of dealing with them. Now, Java has a life cycle for threads, and it looks something like this. So you have this waiting state after the process has been created. This is slightly incorrect, or it's slightly misleading in a sense. There's this method called start, which you can call on a thread. And the method called start actually puts you in a runnable state rather than a running state. In practice, that's a matter of a few microseconds. But the key point is that start makes it available so that the Java virtual machine can actually schedule you, right? And then it can actually run. We'll talk a little bit more about this in a moment, but there's this issue of the start method, the run method. There are other methods like, wait and similar sorts of things that we'll end up using, or at least end up talking about. But there's also a method called stop, okay? And stop is, at least in an unguarded fashion, fundamentally evil. And we will tell you how to get around that. And that bit of code is very important, okay? So we'll move on. I mean, it's very important in the sense that it's often something which is examinable, but it's just very important, right? Because, to, again, sort of give you a preview of what's coming. If you call the stop method on a thread, the way these things are set up, you don't really know what the state is going to be when the thing actually stops. And that is a problem, okay? It's a really, really difficult question here. And the thing that we have to deal with is the fact that if you have multiple threads operating, then the world is very, very different from if you just have this single backbone thread that you're used to. So we have the main thread created by the JVM. I want to emphasize very quickly this notion of the main method. Okay, I've said this to you before, but get it into your heads again. How many times do you call a main method? How many times do you call a main method? 0. Never. Ever. The operating system does it for you. Within a program, we have a thing called the run method, right? You never explicitly call the run method either. So the run method is the main method for the individual threads, okay? If you keep that in mind, you'll have almost no trouble with this stuff. The run method is the counterpart within a program to a main method at the operating system level. Is that fairly clear? It will become clearer as we see it in practice. Okay, most programs you see, particularly at this level, are single-threaded. You only make them multiple-threaded if you have reason to. And basically, the reason that we typically make something multi-threaded is to deal with blocking. And blocking basically involves some sort of, waiting for some user interaction, taking forever to load a file, doing some printing. Or the other reason we use threads, of course, is to get some sort of multiprocessing in place. And so if we have a modern operating system and we have a modern chipset and we have, sort of 8 cores and 16 threads available on the processor, well, then sometimes for particular problems, it's nice to take advantage of that. And most of these modern languages have parallel extensions which enable you to deal with those sorts of things. Okay? So Andrew, who spoke here a couple of weeks ago, his PhD, when he wrote a new C# compiler, part of the stuff that he was doing there was looking at the parallel support for that sort of environment. So the JVM has its own threads. We don't need to know about them, but they're threads. Okay? So garbage collection, the event thread. We also have priorities relating to other threads. Let me give you some very good advice. Never, ever, ever trust a threading priority library, ever, okay? If priority is really, really, really important to you, utilize some of their stuff and write your own guarantees to make sure it works the way you want it to. That's absolute. You'll see it in the tutorials. You'll see it when you look at the examples. You just can't depend on it behaving as advertised. It just doesn't necessarily. Just why, I'm not entirely sure. There are sometimes it's just an operating system variation, but most commonly it's just something where the guarantees have not been fully implemented, and that's the way it is. So we need to be aware of these things. We also need to be aware of some ancient popular culture. So the ancient popular culture here is Lost in Space from the 1960s. And so you have this famous robot going around saying, "Danger, Will Robinson." So yes, this is something which I used years ago when I didn't have to explain the popular culture references. Now with a younger audience, I have to explain it, I'm afraid. So what we have here is a very important warning, okay? Danger. Everything here is different from what you've seen before. And the key issue is that things are asynchronous. Things don't behave the way you think they do, right? Because as soon as you have more than one thread, all the guarantees that you have in your head that this step follows that step go out the window. Sure, on the thread that you've got, the thread that you're looking at, the second step surely follows the first one. But that doesn't take into account the third and the fourth steps, which are on other threads and can be inserted, excuse me, can be inserted at various stages. So if threads communicate with or share data, then there are problems, or there are potential problems. And the point, of course, is that you need to make sure that these accesses and modifications happen in the order that you want them to. Because if they don't, you will get gobbledygook, as you will see later on. Okay? We will show you something that happens when you don't actually deal with this. So Java uses this thing called the monitor approach. Have you heard of quicksort, by the way? Okay? Yep. So quicksort, written about 1962, is still as good a sort for general purpose as any that exist. And Sir Christopher Hoare there, C.A.R. Hoare, he was responsible for quicksort. He was also responsible for a thing called CSP. Anyone know what CSP is? I wouldn't expect you to. CSP is communicating sequential processes, which is one of the first pieces of formal methods around concurrency. So, yeah, he did a little bit, basically, during the course of his career. So the idea, basically, is that when a thread enters this monitor, and a monitor is basically just an object or a section of code which has been designated. And we'll talk about it later, this notion of a lock. But it's not a sensor, it's not a monitor. The name does make it sound as though it's a controller, and that's not the case. That's not the way it works. Okay, and we'll show you that later. It's really very simple. But the basic point is, once we're in that state, once we've reached that particular position in the code and that state, all other threads are blocked until that thread releases the lock. It's very much analogous to the lock-unlock idea that we had during discussions of source control. So yes, for those of you who are not familiar with Lost in Space, there you go. Okay, so that robot there is the one which was always screaming, "Danger, Will Robinson." So the neat bit in all of this is the way we are able to manage it. We're able to manage all this stuff, and we are able to organize so that we can actually have the benefits of massive numbers of different threads, but we're also able to ensure that what we do is correct. So we're organizing two ways of actually getting the thread to run, and we don't really care. All right? So I just want to talk you through this. It's boilerplate code, and it's boilerplate code which you will use again and again. And the basic idea is that you've got to make sure that you have a run method. You put all the things that you want to actually do in the run method. You make sure that you have a thread, and you get that by making something runnable or by having a direct subclass of a thread. And then you call the start method, and away you go. All right, so what's this look like? All right. Okay, so java.lang.thread is the class, java.lang.runnable is the interface. Both of them have a run method, and that's the way we use it. All right, so this is fill demo, okay? Simple enough. Okay, you've seen this before. I demoed it a few weeks ago when we were talking about swing and talking about threads briefly. This one here is the basic code. Okay, I fill, do nothing. All right, so this thing has no threading character. All right, this is fill demo. If I come in here and I actually look at this thing, and I go and actually look at fill demo. Sorry, I've got the console up there for the slide. It's a very simple thing. This is the one which just won't block, basically. It won't allow us to do anything because it's all blocked. Right? So each time I hit this, we just get ignored. Okay? And of course, I can terminate it here, which I will do. Now, the point here is to take something like that where we are doing some work. Now, all of this stuff is in the lecture notes. I'll jump back and forth between this and the lectures. But if you look at the fill method, which you can see in your notes if it's easier for you to see, it's basically just producing those little circles and running them across the screen. Now, what's happening is it's a simple swing method. When I push the start button, I have this action performed event handler, which runs fill, which is this, okay? And then do nothing is just a wait, okay? This is something we'll talk about later. There's a static method on the thread class called sleep, which does what you think it does. Okay, you specify a time in milliseconds, and it waits and does nothing for that period of time. Now, it's a standard swing application, okay? And all of this code is then spread over 3 or 4 slides with a few things in place, like the pause timing, how the fill demo actually works, and so on. And as you see, it doesn't work terribly well. So what we want to do instead is to improve it. And the way we improve it is by saying, well, I've got this stuff, which is the fill. Now, if I were to put this on a background thread, then that would mean that I've got other things that I can possibly do. Now, that point about purity before, in reality, we would do this, if we were doing this seriously, we would do the background on a swing worker, but that's sort of introducing too many things at once, so we'll just take it easy and just have this particular thread and its run. So what you see here is this do nothing, which is the reason that the thing is so jerky, because we're waiting at 100 milliseconds each time, and away we go. the GUI is blocked, right? Because fill is just taking up everything, right? There's enough work there to mean that the rest of the application just doesn't get any response. And so what we're trying to do is to try and improve the responsiveness of the code by using a background thread. Now, the background thread, we will begin by utilizing a thread. And you see here that we've got this threaded fill demo extends blah, 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 okay? And we've got this thread which we're going to call Packer, right? So here's Packer, which is new Packer, and we will see that we can run the thing. All right, so what is Packer? Well, Packer is just going to be a new class which doesn't do terribly much except in its run method. So here you see this public class Packer extends thread. All the rest of the logic is the same. All we're doing is we're setting up this thing to make sure that we have the appropriate panel so that it can actually do the drawing. And then all the work is in the run method. And as I say there, this is fill in disguise, right? So all the logic which was in the method fill is now in the run method. Now, if you look at this then, so do nothing is unchanged because that was using the static access on thread anyway. And so just jump back up here. You've got this action perform method where you've got the new Packer and Packer.star, and away we go. And unsurprisingly, when we run this, it will work quite nicely. I won't show you the code straight away. We'll jump and talk about Runnable first. Now, with Runnable, we have numerous constructors for it, but the basic idea normally is we take a class, we implement the Runnable interface, so Packer is something we can do with, and then when we want to invoke that as a thread, we pass that class that we've created, the new object that we've created, to the thread constructor. And we'll see this in the code. So let's have a look at that. The thread class I'll sort of discuss a little bit more in a moment. But let's just jump and have a look at this and look at packer.java. Okay? So this is the class Packer. And Packer, as we can see, is here it's actually the threaded version. Sorry, we don't have the runnable version. That's only in the lectures. So what you've got is this as set up, and in threaded fill demo, a little bit further down here, you'll see this Packer.start, which means that Packer is now in a runnable state, okay, or it's in a state where it can actually be ready to run, okay? And basically, if you run that, as we saw before, or as you would imagine, we start it up, and that's all happening, but the key point here is that the main thread is still available, and I hit that and it goes straight away. That's because you've got the two threads in operation. So it's a very straightforward sort of thing. I mean, the classical example of threads in operation is an internet browser, where you've got multiple tabs open, or you're printing and so on. You can do all sorts of things essentially simultaneously. So if we come back to the lectures then, the thread class has a number of different methods, and of course the runnable interface only provides you with a run method. That's the only one that you need to worry about. Now, in the thread class we have the run method as well, and we have start and yield and sleep and join and is alive. Now, there are two versions of sleep. One is static. You can just go thread.sleep on a main thread, okay? And that will just pause everything. And that's what you'll use when you're just trying to introduce a delay in a normal program. If you want to make the current thread sleep, so my thread.sleep will make that thread sleep as well. So it comes in two flavors. Now you have this run, which we understand before. We have start, which allows the thread to be available for execution. Can start running. We have the yield, okay, which is a pause, as it says there. We have a couple of others. We have join, which we'll demo a little bit later on, and we have isAlive, okay, which is a Boolean to see whether the thread is still running. So all of those are relatively straightforward and get used. We also have methods like stop, suspend, and resume, which were introduced in the early stages but are deprecated. So just don't use them at all. Particularly don't use stop. So we'll see how to deal with these things a little bit later. Don't use stop because it gives you an inconsistent or an unknowable state. Suspending a locked thread means that the lock won't be released, so that's obviously very dangerous. That will mean that you're going to have problems as well. But there are ways of dealing with all of these, and we'll show you those a little later on. So the main things to remember are run and start. And then when we come to stopping, we'll show you that with a piece of guarded code, which is something which is going to come fairly soon. So what we do is we embed the action in a loop, right? Very oddly. It's an odd piece of code until you understand what's going on. It's a thing called the guard pattern. So you carefully control this loop with a stop flag. You need to be very, very careful about the accesses to that stop flag, of course, for various reasons. If you have other threads which are modifying it, well, you can end up in infinite loop territory very nicely. But you want to make sure that you're able to stop what's going on, okay, to actually ensure that you know what the state of the method is or what the state of the object is when you actually terminate the thread. And we'll show you how to deal with this. So this is a thing called a guard pattern. And essentially what happens is we receive a message that says, yes, we're going to do something and we're going to stop. And we then wait for the thread to finish its current business. And then it's terminated. Whereas a stop is sort of an immediate stop. And that's the problem, because we don't know exactly how far through a set of operations it might be when we utilize that method. So here we have a thing called spawn two threads. All right. Public static void main, we have two threads. Both of them are number crunch threads, which we'll look at in a moment. And we start one, we start the other, and then we call join on one. Okay? So what does the join method do? Well, let's see that in practice. We'll talk about it in a second. So here's this thing called hello name, which extends thread. And it's a very simple thing. What is your name? And then it prints out hello plus your name. And all of that is just file access code. It's all boilerplate. You don't need to worry about it. The key things are in red. We're just grabbing your name. We're printing out hello plus your name. Very, very simple. We move on a little bit further. And here we've got this thing called number crunch extends thread. All right, so just jump back up to the main program. We had one thread called hello name, okay, and we had another thread called number crunch. So there are two different types of threads. So hello name we've already seen, number crunch. All right. Okay, what's going on here? All right. What's it waiting for and how does it end? Well, the first thing you note is that this one has an end method. That's in red down the bottom. And this is the guard pattern that we were talking about before. So if I want to terminate this thread, I call its end method. What happens when I call its end method? Well, the stop flag gets set to true. Okay? So this pattern is very important. So you see in the class at the top there, private static Boolean stop flag is false. Okay? So it's set to false. And then I have the run method. And you see there's stuff going on. And then we have while not stop flag do stuff. All right? You with me? So what happens when I change the stop flag to true? So that while loop fails. Okay? But the important point is not that the while loop fails. It's that the while loop fails and we know where it stops. Because basically what happens here is this end method doesn't have any effect until, you know, if I happen to be in the middle of this log operation or the sleep, That end method does, which will of course be called on another thread, probably the main thread, that operation doesn't have any effect until we get to the bottom of this while loop, right? That's, you know, we finish the log, we finish the sleep, and then we come back up the top to that call to test the condition. And at that point, the condition is false, the while loop terminates, and we are in a known state, right? And that is crucial stuff. The reason that this is important is not the sophistication of the code, which is obviously pretty easy. It's the fact that it means that we know the state when we come back. Okay? Is everyone clear on that? And what happens here? Well, here I've got an int and I've got a double. So what I'm doing is I am repeatedly incrementing I. Okay? I'm repeatedly incrementing I. And then I'm sleeping. And eventually when I terminate, the log of D, which is whatever that value happens to be, the log of the integer, I should say, of I, is whatever D happens to be, math.log. Okay? And you can see, obviously, that we've turned it into a double by using the log operation. So this is the second thread. What's it waiting for? How does it end? Well, we've sort of answered those questions, but none of this makes sense, really, until we go ahead and we look at running the thing. Okay? So I'm going to run the thing. And I'm going to, unsurprisingly, bring this up a bit. So it's not that big piece of code. So what is my name? CAB302. Okay? Now, there are two things I want you to observe there. The first is that, unsurprisingly, it actually said, yes, we've got this name. And not a lot happened, except the log happened. Okay? So what's going on here? Well, I have the number cruncher, and I have the number cruncher end, and I have the one.join. All right? So come back to 1. So 1 is this is hello runnable, which is this piece of code here. And here we see that we've actually got something which is a little bit different. And I've got this system.out.println. And really, yes, it's not actually giving us a lot. All right, so let's actually fix that up and make sure that it has something a bit saner. So we'll make that just to make things a little bit clearer. Okay. Let's run this again, and then I'll make the point that I was going to make. Okay. So here, I'm just going to go CAB302 again, and we get that coming out, right? Okay. Now, I'm going to try and be a bit quicker. Okay? That's about as good as I'm going to get, I think. All right? So, what's going on? So you've seen a pattern there, surely. So as I get more and more psychopathic in my responses to change the thing, to stop it quickly, I'm getting smaller and smaller values. Why am I getting smaller and smaller values? Because I'm quicker, but why? What's happening in the code? Yeah.
Does it run for less time?
Yeah, but why does the loop run for less time? Yeah.
The stop flag thing will be triggered when you enter your name?
Yeah, but it's not, what I'm doing is on a separate thread. Okay? It's all to do... Sorry, someone take it.
So it waits until one thread terminates and then...
Yeah.
That time delay then gets...
That's exactly correct. Why does it do that, though? Do you know at this stage?
Because once you put in the name, you get the thread self-terminates.
Yeah, okay, but the basic point here is slightly different. what I've got here is this thing. I've got four pieces of code which are important here. I have one.start, which starts the name thread. Okay? I have two.start, which starts the number cruncher thread. And then I have nc, the number cruncher thread, .end, which stops the number cruncher thread. But the key piece of code is one.join. Let's see what happens when I remove that. And this will be pretty straightforward. Okay? So basically what's happening with this is we're seeing a couple of things that now happen. The first thing is nc.end gets called straight away. Right? As we've seen, the log of 1 is 0. Why are we seeing the log of 1 is 0? Because thread 2 has terminated. nc has terminated. What's happening with my name now? Okay, see what happened? That thread, the first thread, was still running. Nothing had terminated it. Okay, so what was going on before? Well, join is a very special method. What join does, if I call one.join, that means that the other thread waits until 1 has terminated before it continues. Right? And so what was happening is that was all going on in the background. Okay? That was all going on in the background, and then the main thread continued. Sorry, I probably expressed that badly. One.join was called on the main thread. Therefore, the main thread did nothing until 1 finished. And then once 1 finished, nc.end can be executed. Yeah?
Does that mean every other thread? So you had 3 threads.
So I've got 3 threads. So one.join is called on the main thread. And what that means is that main waits for 1. Thread 2, as you saw before, keeps executing. Right? The important point to note is that the killing of thread 2 happens through nc.end, which is a call on the main thread. Right? So is everyone following me there? Okay. The basic point with all of these examples, and this is a really, really good example. So basically, you've got this code, execute it repeatedly, change it, understand what's going on, because this is the way you understand threads. Threads you can understand theoretically, but there's nothing like seeing it, right? So what you've seen there is an extremely good example of how the threads actually work. And as you saw before, hopefully, some of you weren't necessarily expecting this hello wolf at the end there, right? Because that's the gotcha. That tells you that we've terminated nc.end, but we haven't actually stopped. Yeah, so we've terminated nc by calling nc.end, but we hadn't at that stage stopped thread 1. Yeah?
So if you have 2 separate threads and you use one thread to control or to run off on its own, wait until the other thread is finished to synchronize the thread operations. You get one?
Not sure I do. Just go with the bit at the end.
Okay, so say for example you've got 2 threads, one's doing one piece of code, the other one's doing another piece of code.
Yeah.
And the timing of one being able to be completed, and it may be dealing with a large data file or whatever, the other one might just say, okay, I'm going to grab all this GUI information, and then I have to wait for this.
Yeah. Yeah.
You can run through this thread and then call this thread as a join and tell the second thread that's working on the large file, come back to me when you're done.
Yeah, that's absolutely correct. I mean, that's one use of join. You can also do a similar sort of thing there using the wait and notify mechanism, which we won't really deal with in this class. But yeah, that is a definite use of this sort of thing. You're wanting something to be finished probably because you want to use some of the information coming from the other thread. Okay? But here you see how this stuff is set up. You also see here too that we have this thing over here, hello runnable, which is the runnable version of hello name. So here's hello name. And hello name is this very simple extends thread. All right? And hello runnable implements runnable and has this run method, which happens to be sitting in there. Now, one other notion, just coming back to run two threads. You'll see here that one is a thread, okay? It's new thread, but this thread is created by passing the runnable object, hello runnable, to the thread constructor. Are you with me there? Thread 1 is new thread, but I've passed hello runnable as that constructor. With the number cruncher, same sort of thing. Okay, I've got this new number cruncher, but I actually want that object because I want to call its end method. So that's why that one is not just passed as a new number cruncher to the thread, because you see down the bottom there, I want nc.end. That nc.end, that end method is not something which comes with the thread character. It's something which we have provided. All right, so that's the difference. That's why the two of them are like that. Okay, so that's an extremely good example. I have set the exam. I don't know off the top of my head whether there were questions on this on there, but it's the sort of stuff that we typically look at. If you can understand these sorts of examples, then you really understand threads. If you understand the example which is coming later, a thing called the dining philosopher's problem, then you really understand threads. But that's something which we will deal with after the break. Huh? Yeah.
Today we're given an email saying that we were assigned to we've been working out.
Sorry, for our, the CAB 302, that seems very unlikely.
I received an email saying that we were assigned to
Show me the email, because I've not sent one. By whom, sorry?
Mike Collins. Should show up soon. Miles College.
Okay. So, right, so he thinks you're working with him. Is that the story? Or are you Chris? Or?
No, on neither of those. My name's Lachlan, he's Carl, so we've been working in a group since last year.
Yeah, okay. So what's the issue?
Does this mean that I'm being assigned to this guy here?
No, I'd say he's just accidentally sent He's accidentally sent it to the whole list instead of sending it to me. So, yeah, don't worry about it. Yeah. Just send me the email. Yeah, cool. All right. Okay. Okay, we'll get back underway in a sec. This is my .cab302 pairs folder in Outlook. So as you can see, some of you will actually be able to see your names. The key thing I'm looking at is this, which says items 92, which is a great deal better than the 50 or so I saw the other day. But that's still significantly less than enrollment of the class divided by 2. So if you have not sent me an email to this effect, that you are in a pair, please do so sometime today. And other than that, I will start allocating people to pairs. Okay? So please have a look at this, and you should actually be able to get some idea of what's going on. This is the apologies for the to Jake and Thomas for using them as examples, but basically that's what you get. All right. So that's the sort of email that I'm trying to get from people. All right, let's move on. So what you saw there was an example where we used the Runnable Interface. This is pretty much a summary of the differences. We note that Runnable specifies run. Okay, much lower overhead than extending thread. The basic point, as I showed you in the code example, is that you've got to wrap a runnable object in a thread constructor. It's a very straightforward notion. And basically, when you change these things, this is what it looks like. So you have a run method. So implements runnable, public void run. The usual stuff is in here. Okay, and that's exactly the same as we saw before, except that it implements runnable. The actual code is the same. The actual execution of it is different because of the fact that you have to wrap it in a thread, as I said before. But really, there's no great difference. Okay? So in order to get the thread, you see here where we use the thread wrapper, which is what I explained before the break. And then you have this NC down the end, which is why you have NC implemented, if you like, or initialized on a separate line. All good. Okay, service threads, well, we need to know they exist, but that's about it, really. Okay, so the JVM has service threads. You can also have service threads in your own programs if you want, and you basically just turn them into daemons. Okay, so a daemon in computing, okay, they use the name daemon because, of course, a daemon is something lurking in the background. Might occasionally destroy you, but generally these are helpful daemons. And these helpful daemons are there to, monitor changes and, to do things in relation to printing and accesses and so on, logging and so on. So there's really not a great deal of, sort of intellectual challenge about them. The main aspect about them is that they're there to monitor things. So if you're logging, if you are, have something that's there to see whether there's any print jobs, it's just something that polls every so often. And so the example here is using a daemon thread on each port in some sort of server so that it's listening for connections or for connection requests. And when it gets connection requests on that port, then of course it actually invokes not itself, but a worker thread which will go away and do the work that's required in order to fulfill that particular request from the client. So a fairly straightforward thing to look at. Okay, so the basic thing, if you want to turn it into a daemon, well, use the setDaemon method. If you want to know whether it's a daemon, you use the isDaemon method. Okay, so it's a nice little name, but its usage is very straightforward. Okay, scheduling tasks. Well, scheduling tasks, basically, you can use all sorts of things, but the way we do it normally is via a little process called timer. Okay, so there's timer task and timer from java.util. The basic approach, if you just want to delay something, you just use thread.sleep. Okay, and that can be used at any time, just stops everything. You can also have a thread-based approach for a particular scheduler that you want to use. So in those circumstances, you have a thread, you put it to sleep for a while, and then you allow it to do what it's supposed to do. But in general terms, if you want something which is just, a normal method call or set of method calls, just use timer, okay? Because timer is much easier to work with. So it's something which comes out of java.util. It's very straightforward. And this is the run method. And the run method has a message. And you see that the timer task, once again, utilizes a run method. And we will see what happens. Okay. We create a timer. Okay. And we then try and do things. So what have we got here? All right. So here we've got hello, hello again. Do you like my hat? I do not like that hat. Goodbye, goodbye. So it's a rather formal 19th century type conversation. It's not really something which is particularly demanding, but it's a reasonable enough idea. So what I'm doing down here is I have a timer. Now, I've created a timer as a daemon thread. Okay, that's why it's got true in the constructor. We don't use or see timer anymore, but it then sets up a background timing thread, as you would imagine would happen with something which is called timer. What we then have to do is to just go through with this particular scheduling. And so what I've got here is 1,000, 2,000, 3,000. All of these things, of course, are in milliseconds, right? So everything uses a long int, okay, an unsigned long. All of the specifications are in milliseconds. If you see something which is 1,000, that means it's a second. So 1, 2, 3, 4, 5, 6. We go over onto the next slide. And then we have this thread.currentThread sleep for 7 seconds and at the end of the conversation. So we've scheduled messages at 1 second intervals and then a long wait for the end. Or is it? So let's have a look at it. And sorry, what was this one called again? We called it schedule tasks. Okay. So there are a few here. Okay. So here's schedule tasks. Let's run it up there. Let's run the thing and see what happens. Okay. Didn't we have a delay of 7 seconds? Didn't feel like a delay of 7 seconds, did it? Of course, it was designed that way. What was happening? Why does it appear correctly, as it happens, that we have a delay of 1 second instead of 7 seconds?
Or was the thread running in the background and the 7 second counter was already running to finish by the time the conversation ended?
Basically correct, yeah. There are two separate things going on here. Okay? What we've got is something here where we have this try thread.sleep system.out.println end of conversation. Right? Now all of this is on the main thread. Public static void main, string args, da-da-da-da-da. The scheduled tasks, well, they're all set up on the timer. And so, in fact, the delay of 7 seconds wasn't on a background thread. All the timer stuff was on a background thread, right? And so what we're seeing here is something that's happening where all of that stuff is happening on the background, and then we have the final little bit of the main thread, which had been waiting for 7 seconds to print this thing out. And so you get this effect that everything's actually, sort of scheduled appropriately. So that's a fairly good example as well. Okay, so we've seen that, and we're now on to the gory question of thread safety, synchronization, and to a lesser extent, thread communication. Thread safety, oh boy. Okay. So these are essentially you always sort of think of, the 4 horsemen of the apocalypse, right? Pestilence, famine, war, and death. Well, here we've got something pretty close. Race conditions, deadlock, starvation, and live lock. So think of them as these, it's a scene near the ford at Rivendell or something like that, where you have this amazing collection of black riders which are approaching, bringing race conditions, deadlock, starvation, and live lock. Whatever, they're going to kill you. And it's a very difficult thing to deal with at times. The main thing to understand is, as soon as you have asynchronous access to shared data structures, you have potential evil. Right? What happens is you must have some understanding and some mechanism of control to make sure that those accesses happen in the way that you want them to. So race conditions and deadlock and starvation and live lock are very, very important things to understand. So we'll understand a little bit about them as we go. So what is a race condition? What is deadlock? What is live lock? What is starvation? All right, so the race condition is really all about how we have competing processes trying to do, well, not necessarily trying to do the same thing, far from it in most cases, but they're trying to access the same thing and make changes. And the logic, the state of the system and the output of the system will depend crucially in many cases on the order in which that happens. And the key problem with a race condition is that, it's important to understand this too. There's an element of randomness in this. I can have a race with Usain Bolt, right? And we know who's going to win that, right? There's no doubt that he's going to get there before me. So that's not a problem, right? The problem is when you have people who are basically at the same sort of level running, right? And one of them might win or the other might win. So if you had, unless he breaks a leg or something, he's going to win, right? So in those circumstances, you know what the outcome is going to be. There's no problem. The race condition has to have uncertainty. If you don't have uncertainty, you don't have a race condition because you know the outcome. So here, we need to know which thread gets to the value first. The thread's race, if you like, to modify the value. Okay, so the problem, of course, is that we can't predict the state of the variables which are affected because we don't know which thread got there first. And that, of course, is a problem. Now, there are various ways of dealing with this as well. Now, this thing here, there's an additional problem where this notion of a volatile keyword which gets used on particular variables. This is a slightly, it's obviously related, but it's not entirely the full story. The idea of a volatile keyword is to ensure that threads go straight to the source and don't locally cache a particular value. So that means that they're working with the one which is up to date. All right? So this is a related and additional problem where you might actually be working with a value which is out of date because you're relying on an access. Now that doesn't solve the race condition, but it does at least mean that you're aware of its effects straight away. So here's an example of how these sorts of things might actually work. All right? So here's a public class stoppable task extends thread. So here I've got private volatile Boolean please stop. Now, this is a situation in which the race condition is a big problem This is a situation in which the use of the volatile keyword does actually stop the race condition from being a problem. But it doesn't actually, it's not something which necessarily solves all race condition problems, which is what I was trying to say before. So here I have this public void run, while don't please stop, or while not please stop, do some stuff. Public void, tell me to stop, please stop is true. All right. It's a beautiful example. Why is it a beautiful example? It's simple, absolutely, but it's still evil. Why is it evil? It's all explained at the right there. Just see if you can see what's going on. The basic point about this, of course, is that if you don't, there's a prerequisite that you need to understand, and that is that the loop, this while loop, being run on a particular method, being run on a particular thread, is going to be run on a thread which is different from the thread which we'll call tell me to stop. Okay? And there's nothing on the thread which executes that run method which is going to change the value of please stop. That's the background you need. From there, it's all pretty obvious. And the basic point from there is if the active thread, the run thread, if you like, if that thread were allowed to cache please stop, then we could have a slightly long experience with that while loop. Why?
Because it would always be stuck at true.
Exactly. So, well, I mean, please stop would always be at false. Not please stop would always be true. And therefore, we'd just be cycling around and never, ever stopping until the whole thing was terminated, right? So the point is that each, and if you're not with the background here, each thread, like just as each process can have its own local memory, if you like, so each thread can have its own local memory, have its own local variables. And so what you're dealing with here is the interaction between those two, between these two threads. And volatile says, go back and check it. Okay? So you don't have sort of a local copy of it. And that's what's going on here. So it's a rather nice example. It's a very simple example, but it's also one that illustrates a very, very evil problem. And it's one that you have to deal with. The key point in all of this also is understanding, as you saw in the NC example earlier, that you really better have the control on another thread, right? If you have the control on the same thread, well, that's not necessarily going to work that well. So you do get those variations. Like if you've got a background thread, it's a background thread for a reason, so your control will be on the foreground thread. So understand how that works. Here's another example, a quite evil example too, quite a simple one. But volatile doesn't help a lot here, right? Why doesn't, what's going on? Anyone explain the example? Yeah. Okay. Yeah.
Thread 1 can pop an element, and then thread 2 can pop an element, but thread 1 already made the stack empty, so thread 2 is trying to pop something that doesn't exist.
Or alternatively, yes. Yeah. So basically, the point, of course, is that you have a stack. It's a shared data structure. Both threads have access to it. There's a limited number of items on the stack. One is guarded, one is not. So ignore thread 2 for a moment. We never have a problem, okay? Because basically, stack.pop on thread 1 will never be executed if there's nothing on the stack, because the guard condition will get it, right? But the problem, of course, is that thread 2 doesn't actually have that. So thread 2 can call stack.pop. But the volatile condition that we had before, the volatile keyword, doesn't help us. This is a method call, right? So basically, we've done a method call. The state has changed. We're dead, okay? We've got a runtime exception. There's just nothing we can do about it. So with that bit of code, we need some alternative method to deal with it. So thread safety is a very, very big issue. If I have something which is thread safe, what that means is that it belongs to one thread alone. Okay? That means that we can't have any of these conditions that we're talking about. Different threads may, if necessary, different threads maintain their own copy, which brings about synchronization issues, but that's still synchronization issues that we know about. So an instance variable and a static variable, well, they're not thread safe. Local variables necessarily are because they're created on a particular thread. And that's one of the things which I was referring to before. So each thread has a separate storage area for locals that's kept separate. It's maintained just like you do with an operating system process. And so it's not possible to have asynchronous updates because all those updates are happening on that one thread. Or at least if they were updates which were coming from another thread, they would have to be processed and interpreted by this thread which has control of that particular piece of storage. Okay? So that's the game, right? We need to have this. So instance variables and class variables. So are these problematic? Yes. Instance variables are problematic if we happen to have threads, more than one thread, accessing a particular object. Okay, that's an instance. There are ways of dealing with this, as we will see in a moment. So synchronization through the use of the monitor approach is the way generally of getting the necessary safety. Class variables, never. Okay? Neatly summarized in this one line. Not thread safe in your wildest dreams. Why? Well, basically it's accessible to everything because it's a class variable. You've got one instance of that class, you've got one of these. So, and emphasize the point, you've got one of these. Right? So there's only one copy. That's all you can deal with. Don't ever rely on it. You basically cannot ever rely on that being thread safe. If you want to manage those values, you've got to manage them some other way. Okay? Okay. Dining philosophers. All right. Who's heard of the dining philosophers problem? Okay, one or two. So the dining philosophers problem is a very famous artificial, pathological, if you like, problem, which was introduced by Edgar Dijkstra. You've probably heard of Dijkstra's algorithm. So for finding shortest paths and so on, well, that's the same Dijkstra. So Dijkstra's problem here is set up so that you have a bunch of different philosophers. He chose some that were his favorites for various reasons, and for whatever reason, they were all eating pasta. Now, you may be very facile pasta eaters. You may be able to take a single fork and bundle it around and eat the pasta just off the one fork. That's not the case here. The assumption here is that you need two forks. All right? Note the number of philosophers. Note the number of forks. Note the number of dishes. Can anyone see a problem? If you need two forks to actually eat, well, some of these people are going to be very, very well satisfied, and some of these people are potentially going to starve. Okay? So the whole idea here of this problem is to illustrate contention for resources. Okay? So they're either thinking or they're eating. Now, there are 5 forks, and to eat, a philosopher must pick up the fork to the left and the fork to the right. And the philosophers, of course, are threads, and the forks are, one on either side. They're shared resources. So you've got the philosopher, fork, philosopher, and so on. And basically, it illustrates everything. So you have this notion of deadlock, which is contention for resource. So basically, and this is probably the thing which will happen most commonly. So it's all random. When you simulate this, it's all random. But basically, you have a philosopher, and what will happen is that they're assigned. Each philosopher has the ability to hold a left fork and a right fork. There are only 5 forks to go around. You do a random assignment of the forks, okay? And if this philosopher here has 2 forks, Well, that means the philosopher over here, even if he's able to grab one there, and the philosopher over here, even if they're able to grab one there, they're stuck waiting because you've got the fork I need. And so what's going on each time is this notion of deadlock. It would be the most common thing which happens, which is the notion of deadlock. Right? So what happens with deadlock? Well, we're blocked waiting for a resource which is held by another blocked thread. So in other words, you've got this situation. Well, sorry, I didn't explain that correctly. It's deadlock truly occurs when the other one is blocked. There's one where you have some sort of contention for resources where you can't get access to it because the other one is executing and doing stuff and will eventually release when they've eaten enough, perhaps. But there's also a situation where you have a canonical sort of problem where all of the philosophers manage to pick up one fork. And that means they're all blocked, they can't do anything, but they're all waiting for a fork. And that's deadlock, because they're blocked, waiting, but the thing they're waiting on is also blocked. And that is, of course, a truly awful situation because, short of restarting everything, no progress is possible. So live lock is another contention problem, which is often explained through the use of a thing called the corridor dance. Okay? So the corridor dance for the excessively polite and stupid. Well, the essential point here, as we say, a thread acts in response to another thread and makes no progress but is not blocked. So what do we mean by that? Well, we want to actually see that the thread states can and do change, but we just don't make any progress with them. So what's the corridor dance? Okay, a corridor dance is basically sort of a semi-humorous term. What's meant by it? Yeah.
Where two people are walking towards each other and one goes left and the other person...
Exactly right, yeah. So basically what's happening is you are exchanging one pathetic state for another pathetic state. So basically you're coming this way, so whatever happens, they just sort of move in the same way and continue the blocking, if you like, but there's never any resolution. And so in the dining philosopher's problem, this is something which arises through a mutual exchange of forks. So what can happen, of course, and this is a perfect example, start from the deadlock situation that we had a moment ago, right, where we had a state where we've got 5 forks, right? Each of them is assigned, each philosopher has one fork. So suppose that all the forks are in the left hand, okay? So suppose that each philosopher passes the fork in his left hand to the right hand of the philosopher next to him. What happens?
Everyone has one fork still.
Everyone has one fork still. And you can continue with this ad infinitum if you wish to. Right? The key point about it is that you're not getting anywhere. Okay? And the starvation is, of course, the one we were talking about at the beginning. Right? So starvation is when you have someone, so basically it's the rich and the poor. You basically have some of them who actually get, obviously you can have a situation where 2 philosophers have 2 forks and can eat until they, reenact Mr. Creosote or whatever from various films, and you'll see that then one fork remains unused, and of course the remaining philosophers can't do anything. So they're starved, the 2 are sated, and that's really all you can say about it. So there's a variety of possibilities here which are illustrated in a fairly straightforward sort of way, and it's something which we have in the pracs for you to have a bit of a look at. If we get time, we'll demo it as well, but I want to talk about some other things. So synchronization is how we solve some of these problems. So how do we synchronize? Well, we use the monitor. Once again, the monitor is not a sensor. So what we're doing, you need to ensure particular orderings for particular applications. So, the share trading scenario is a beauty. Okay, place an order to sell the stock, buy the order, but it depends on the proceeds of the sell order, so you better not get them in the wrong order, okay, unless, people want to pay a lot of money for credit. And we ensure that only one process occurs at a time, all right? It's a very straightforward thing to happen, but we need to do it so that we have control of that ordering and we can mandate and guarantee that ordering actually happens. Now, the way we do this is through the use of the lock. Now, locks can happen in two ways. You can have an object lock or you can have a class lock, okay? So the object lock and the method lock, as we will see. So this is a thing called jumbled message, which we will go ahead and demo in a moment. But have a look at jumbled message, and it's important to sort of understand what's going on. We've got a whole bunch of setup here, all right? And we use a volatile on the stop flag, but that doesn't help us necessarily here, as we will see. So public static void display message, it helps us in being able to actually stop the thing, but it doesn't actually help us in a couple of other ways. So here I've got a thing called display message. So we grab a message, and with this particular message, we print it out, jm.message.character at thread.currentthread.sleep50. Now the problem, of course, is we're going to create a bunch of threads. And as we create a bunch of threads, they're going to be at different stages along that message when they print out. And that's why we're going to see a problem, because we don't have actual control of what's going on here. So if we look at this, we have the run method. So display message this, thread.currentthread sleep pause time, and away we go. Right? It's very straightforward in that sense. And we will have this run method coming from multiple threads. We also have this finish method, which will be called on the main thread, the stop flag being set to true, which we've already made to be volatile, and away we go. All right, so this is the main. So here I'm setting up, really as simple as just two threads, okay? M1, M2, and away we go, and we have a particular thread sleeping. So what actually happens? Well, here we go. Let's go with, where is it? Jumbled message. Okay, so let's just run the thing. You've seen the code, basically. It goes through here. It's pretty much as described, okay? And we run it and see what we get. Okay, so it's relatively compelling. You get intermixing of the two threads, right? And consequently, what actually gets pushed out is very, very different. And the difficulty, of course, is that these accesses are not taking place in any sort of controlled fashion. What's happening is that it just depends upon which thread has access at a particular time, and we have no control over which thread is actually making those accesses. Now, the way we get around this, and I'll do this in the code, even though we discuss it in the lectures in a moment as well. If you look down here in the code, you'll see that there are two versions. So here I have one version, which is to use is basically just to synchronize the method display message. Okay, public static synchronized void display message. Okay, now that synchronized keyword means that only one thread can have access to that method at the one time. The scope of that lock is imposed by the fact that it's a method level keyword. So what that means is that we're only operating on that particular method. That's the only thing which is restricted. Generally speaking, use the synchronized keyword very sparingly and use it on the method that you are wanting to control. The alternative approach is to use a thing called an object lock. And the object lock allows you to operate with just a particular piece of code, even within the one method. You can do this at a whole class level as well if you want to, but that's generally not a particularly good idea, because synchronization has its overheads, it holds things up, and so you only want to use it when you absolutely have to. And this is this strange notion of the object lock, all right? So what we're seeing here, private static object shared lock is new object. Okay? Now, that object has no semantics, it has no function, it does nothing, but it does provide a reference. Okay? And the reference is why it's there. A little bit further down, within the method display message, you'll see synchronized shared lock. And you see that there's a brace, okay, synchronized shared lock with a brace there, and that closes after system.out.println. You can use either, but that shared lock, you know, the use of the object lock, that enables you to have slightly better control, slightly more precise control of the use of synchronization. So if you've really only got a small piece of code that you need to synchronize, use that, because that, you know, that doesn't mean that you have to use a whole method or a whole class. So if we go ahead and look at this then, we can use either of these methods to actually make it work. So we can do it, and all we have to do really is to come in here and do a bit of commenting out. Oh, let's just do this. Okay, so that's now gone. I've now got synchronized void. Let's use the object one. You can do both, and I'll let you run the other one yourselves. They have exactly the same effect. Rather irritating, but...
You can highlight them and press Control /
Oh, okay. All right. Well, I'm probably almost there now, so I'll just use this. Okay. And anyway, that's now available. I will save it. I will run it. And what you'll now see is bonjour, hello, bonjour, hello, bonjour, hello. Okay? So it's a very compelling demonstration that it actually works. Right? The key take-home message for all of this is synchronization is very valuable. Avoid having to use it at all if you can. If you do have to use it sparingly. Right? But don't ever just trust to luck on these things. If you've got multiple threads, try as far as possible to make your code thread safe so that you never have to use synchronization. But where you absolutely can't avoid having some shared state, then use synchronization to make sure that that happens in a controlled fashion, and make sure that you use that access sparingly because it's not without its overheads. Yeah?
Can you just repeat scenarios where you use class locking and object lock, or what do you do?
So basically the method level lock, that gives you synchronization for the whole method, right? In the case that we have here, there's no real difference because the use of the object lock is on a very small, on this small piece of code, which is practically the whole method body anyway. But the object lock is something that you could use when you've got, a very long method or quite a substantial piece of code, and you only want to use it on this little bit. So it allows the control to be a bit more fine-grained. There's not a vast amount of difference between them apart from that. So it gives you the result that you're after in the end. Okay, a little bit more. The key point, of course, is that you have multiple threads accessing the state. There's the example, just to remind you. So you have the class lock and the object lock, the two that are in the code that we saw before. Basically, you want to have just a bit of guide there, which I forgot to mention earlier. Essentially, the system is using the reference, but if you don't make that object final, then of course someone could conceivably use that variable name and actually instantiate another object on it, which would change the reference. So that could lead to problems. It would be an incredibly dumb thing to do, but that doesn't mean it's impossible. So you've got private final static object shared lock. There it is, shared lock, and it's used. That's the object lock. The top one is the class lock. So both of them you've seen in the code before as well. And I'll leave it up to you to run the class lock version yourself so that you can see that that has the same effect. So the basic point about it is just be very, very careful in using it. It's, people get hung up on this stuff and they say, well, I need to be super defensive about everything and have the lock everywhere. And then they wonder why, hello world takes half an hour. It's not what you want to do, right? You want to be very, very careful about this. You only want to lock the code which is necessary to be locked. You need to also just understand that once again, you don't sort of set up this stuff and control it. As with the main method and the run method, the use of the lock is something that you set up and let the system manage. It's not something that you have to control actively yourselves. And that, of course, is a very, very good thing. So there are a few levels of synchronization. You can do it at the methods. You can do it at the class and instance methods. And, of course, you can have none at all if you really want to. The main point, I think, is to think about what it means to have the lock at a particular level. So if you're doing something with an actual method, right? If you're doing something at an actual method level, then that means that you have some sort of control over the variables which are inside, but it's not something where you're necessarily having control over all of the instance methods. So you need to be aware of what sort of granularity is required. Okay, your final point, this is thread communication. I'll just skip over this very briefly because it's not that important to us at this stage. It is important to know about it, but object provides a whole bunch of facilities, wait and notify all. And this is generally done in the context of a producer-consumer sort of example, where you basically think the producer-consumer case study or pattern, if you like, is one where you have someone who's actually waiting to get something from multiple sources, and the point is that that object is probably not doing anything. So you've got a consumer thread which is doing nothing. It's waiting to hear from a whole bunch of producer threads that they've actually produced some stuff. And you would generally regard this, this consumer thread as being in some sort of wait state. Now, the way that wait state, which is a block state, as we're saying here, the way that wait state is lifted is on notification from another object. And Java provides quite straightforward APIs to allow you to do this. So you can have a particular thread, okay, you can have everything put in a wait state so that nothing is happening. And what then happens, of course, is that we're waiting until we hear from someone else or from some other thread. And that happens through the use of a notify and also through the use of a notify all. Now, these particular methods are, once again, they might not necessarily provide the level of control that you're really after. So you may decide that, in particular, the problem, of course, is that when you notify, you get a wake-up call. So notify all sends the wake-up call to all blocked threads, but you don't necessarily have immediate control over which one decides to wake up. So if you want to have that sort of control of the other threads, then you need to schedule that explicitly yourselves. So there's a problem in the sense that these methods can't be overridden, but you need to have some sort of logic inside the threads to make that happen. So for that reason, they're perhaps not as nice as you would like. And so people tend to operate in other ways for particular applications. Okay, so using wait, the basic point here is that you want to just keep some sort of control and not sort of waste cycles, if you like, while you're awaiting some particular response or some particular process to terminate. So that's not something which is going to be hugely examinable, as I said before. The problem with this notify, it's really kind of odd. You say that you can, like the API says that notify lets you notify a single thread, okay, that basically we're ready. but you can't use it to notify a particular thread. The JVM decides which thread actually gets activated, which has always seemed to me to be a somewhat bizarre sort of limitation, and hence my comments before about these not being as useful as they might be. Okay, and notify all just wakes up all waiting threads, so you've got that collection of them all. I suppose in those circumstances you can decide which one's going to work and shut down the others. But it's a little bit inelegant to be truthful about it. Okay, our final point then, threads and swing part 2, which will lead to an extra practice sheet. So this is a summary of some stuff which you need to be aware of for assignment 2. It's some stuff which I'll give you a sheet to work through so that you can get on top of it. The basic point, I'll show you some of the code in a moment, but the key issue in all of this is that swing and most GUI, we're going to run out of time, so we may not get to the code, but the key issue is that swing and most other GUI libraries are not thread safe. In fact, you can argue about whether it's possible to have an event-based control system which is thread safe. Now, the events are processed on the EDT. Okay, so EDT is the event dispatch thread, and the event dispatch thread, or dispatch thread, depending on how you want to spell it, is crucial to the operation of any sort of GUI. And the point here is that you don't get that as a matter of course. You have to explicitly invoke it, and you explicitly invoke it by using this thing from the Swing Utilities class, which I'll show you in a second. Now, if you have a task that requires a lot of work, much as we had before, only more so with the fill demo, in those situations you will use a swing worker. And we're not going to deal with swing workers because we don't really need to, but I just want to make you aware that a swing worker talks properly to swing and its thread management behavior, and this is very well discussed in this tutorial in the tutorial trails, and this one is concurrency in swing, okay? But we won't deal with that. Working with the EDT is something, however, that we want to deal with properly. And this is what you'll see. So this is the main sort of boilerplate code. So I'll describe the basic idea of the worksheet is just to show you how to make sure that the responses are also going to be handled by the thread. Okay, so there are particular idioms for doing that, and I just want to make you aware of those. So here we have public static void main, as usual, and the important point is this javax.swing.swingutilities.invoke later. There are various other invokes which you can use as well, but invoke later will do in almost everything we're dealing with. And what you're seeing here is an anonymous class, new runnable, right? That's that syntax that we saw for the action listener when we were dealing with the swing lecture a couple of weeks ago. So the public void run, myFrame, frame is new myFrame, All of that is just the GUI creation code, right, which you'd normally have in a main method. Here, it's not so much in a main method as in a run method within an anonymous class, which is invoked from the main method. So the way the Java tutorials say this thing is that they have 3 threads, or 3 types of thread. We have an initial thread, which is the main thread, which is to set things going, and to which you can return at the end if you wish to. You then have the event dispatch thread, which does all the event handling, okay, or should at least do all the event handling. And then you have a pool of background threads which are accessed via and created and accessed via the Swing Utilities, the Swing Worker classes. Okay? So that gives you an overall picture of the sort of thread handling which exists within Swing. I will give you another sheet which you should work through and shamelessly steal for assignment 2 in order to get your thread handling within that application correct. Okay, that's pretty much all I want to say for the moment. Any other questions? My final parting message is to get your partnerships sorted out if you can. If you are desperately stuck for a partner, you can start emailing me late this afternoon, okay? And I'll try and put you in touch with people.
Hey, Jim.
is there a way that we can run a test that throws an exception multiple times in a loop?